see from the figure that I have shown, I'm showing on the slide now. This is the isotope for non-porous and porous. This is still we are discussing on the BET isotope. These are all BET isotope. Okay, so from BET isotope, you can actually differentiate from the shape of the isotope. You can differentiate whether the absorption occur on porous or non-porous materials. So what is non-porous? What is porous? I think you already know. Normally, if you have a flat surface, or a rough surface, a bit rough surface, these are all non-porous surface. But if you have a surface which are like if you have surface and then you have pores, what you call as internal pores. These are the normal surface, but you have internal pores, and the absorption can occur in these pores, right? Absorption can occur in these pores, so these are called as porous materials. Right? So we can actually differentiate the isotope. What is isotope? Isotope is the plot of the amount absorbed. All right. This is written as Q absorbed, right? As you can see here, versus the relative pressure. Versus relative pressure or versus pressure. Versus pressure also, you can use versus pressure also, but normally we use relative pressure. What is relative pressure? Is the pressure of over the saturated pressure, over the saturated pressure. So that's why you can see the value is between 1 to 10. Sorry, 1 to 10, 0.1 to 1.0. Cannot be more than 1. Okay, it's because the pressure shouldn't be more than saturated pressure, right? Okay, so this is 0.1. You can see here, this is actually 0.1 to 1.0. So the largest is 1.0. Okay, so you can see that the for non-porous materials, it is the absorption occur when you start giving pressure. What happens when we give pressure? Meaning that we actually get the gas or the adsorbate to absorb on the surface. So when you give pressure, the absorption start occurring. You can see here, the absorption start occurring, and you can see the rise in the amount absorbed. Okay, the rise in amount absorbed until it reach what you call as the monolayer absorption stage, right? And then if you further increase the pressure, so the absorption will keep on occurring, and until it reach a situation where the absorption form back condensation. That is where this is where these the reaction cannot go any further, and that is where you can read the saturated pressure, right? And then after that, what you do, you can do desorption. You can do desorption by lowering the pressure. By lowering the pressure, so you can see that this is increasing the pressure. You can see the arrow there, the arrow there increasing the pressure. And then after increasing the pressure, what you do is decreasing the pressure, right? Decreasing the pressure by reducing the pressure from high pressure to low pressure. And by doing so, what will happen is that the absorbate that is absorbed on the absorbent, for example, you have when you give pressure, you will get the absorbate to absorb on the surface. They form absorption on the surface. But when you give lower pressure, what you should see is that the adsorbate is taken out from the surface and it is dissolved from the surface, right? So by lowering the pressure. Okay, so that is what will happen. And for the case of non-porous materials, the adsorption and desorption process will follow the same line. Will follow the same line. Meaning that, what does it mean? That means that the amount of pressure that you need to absorb certain amount of substrate, right? The amount of pressure that you need to absorb certain amount of substrate or a certain amount of adsorbate is also the pressure you need to dissolve back this the same amount of adsorbate, right? So meaning that you're going to follow the same, going to follow the same, going to follow the same route on the assertion. So that occur for the case of non-porous material, whether it is like this, right? Whether it is a rough surface or it is a smooth surface without any pores, that is considered as non-porous surface. But if you have pores, the different situation will occur where the adsorption will not only occur on the surface, on the non-porous surface, but it can also occur inside the pores, right? So if the adsorption occurs inside the pores, the adsorbate that has been absorbed inside the pores, it is quite difficult for them to be taken out from the pores. Quite difficult for them to be taken out from the pores, and to take out this adsorbate from the pore, you will need lower pressure. You will need lower pressure than the pressure that you applied earlier for the adsorption. Okay, so that's why you can see from here, from the graph there, for the porous materials, the adsorption occur. This is for the adsorption, right? For the adsorption, follow this line, but for the adsorption, it follow a different line, right? So this shows that you will need a lower pressure than this the pressure to. If you read, for example, this is the amount absorbed. This is the amount absorbed. So, right. So this is the amount absorbed. Or you can also like say you can take a line. You can take, rather than taking this horizontal line. Let's take the vertical line, for example, at certain pressure, right? At certain pressure, you can see at like this pressure, right? So the amount absorbed and the amount dissolved are different, right? So the amount absorbed and the amount dissolved are okay. So the amount absorbed, dissolved are actually higher. The amount dissolved are higher compared to the amount absorbed at certain pressure, right? Okay, so that shows that you will need a lower relative pressure in order for you to be able to dissolve this the amount of adsorbate that is trapped in the pores, right? Okay, so you can read. All right. So rise, move, rapid, and intermediate and hysteresis loop occur on desorption. Okay. So all right. So the difference between these the adsorption pass and the desorption pass is called hysteresis loop, right? It's called hysteresis. So you can see this is the absorption and this is the desorption. So it forms a loop here, and this is called as hysteresis loop. And so from there we can actually also get the information on the pores, on the size of the pores that is involved in the absorption. Right? So we need we can use, and from the type of hysteresis loop that we get from the absorption on porous materials. Okay, let's go further to see what type of pores that we can get. So these are the type of pores that we can get, right? So we can get mesopores, and we can get micropores, all right? Mesopores or micropores. Micropores, it is should be less than 2 nanometer, the micropores, right? So this is for nitrogen absorption. We can use nitrogen absorption. You can also use the other adsorbate, like you can also use like argon, for example. If nitrogen is not suitable for the absorption, in your case, you can also use argon, for example, for the absorption process, and you can also get the same classification of the pores. Right? So this classification is given by IUPAC. Okay? Given by IUPAC. What is IUPAC? Anybody can tell me what is IUPAC? I'm sure at this stage you already know what is IUPAC. IUPAC is a big organization for chemistry. It is International Union of Pure and Applied Chemistry, right? Okay, so the classification given by IUPAC is that for micropore, the D, or the diameter of the pore, should be less than 2 nanometer. All right, it's very small pore. That on with that value, only the material can be classified as having micropore, right? So if the material has the pore within less than 2 nanometer, if it is between 2 nanometer to 50 nanometer, it's classified as mesopore, meso, and if it's more than 50 nanometer, it is macropore. So macro. So normally we will see macropores, very big pores. We're not able to see mesopores and micropore. You need high magnification scanning electron microscope to be able you to see the micropore. Normal microscope, like probably you have heard about SEM, scanning electron microscope, or FE is SEM, field emission scanning electron microscope. But these two microscopes will not be able you to get or to see the micropores and mesopores. You will need higher powerful microscope, scanning electron microscope, like HR10, high resolution transmission electron microscope, or for some higher version of transmission electron microscope, so you can get to see the pores. But you'll be able to get the pores only by doing the absorption. So by doing absorption, what you'll know is that what type of pore is there in the materials, and how much these pores in the material. For example, you get this like diameter, and also this pore, the volume of pores, and then it will give you the distribution of, for example, how much is the pore for less than like this is like say 2 nanometers, and this is 50 nanometers, and then you can get the idea of what pore is the majority pores in your materials. Okay, all right. Okay, type of acertum that has been classified by IUPAC. These are the type of acertum that classified by IUPAC. There are 6 type of acertum classified by IUPAC based on the different type of pores. The first one is for microporous material. You can see that the microporous material, the absorption occur very fast at early stage, right? And then after less than like 0.1 relative pressure, these isotope already saturated, and it form a horizontal line, which shows that the absorption is already finished for this type of substrate or this type of adsorbent, which only contain micropores, right? Microporous material. Okay. So for non-porous materials, this is non-porous material. You can see this is the same as we have seen in the example before this, right? So the absorption occur, and you get absorption, and then the absorption can further occur to the surface until the saturation situation, or until it form condensation, right? And then this desorption will also occur on the same line. Okay, desorption will also occur on the same line. The same as the micropores. You can see that desorption and desorption line are actually overlap. Right. So you have got other type of materials, other type of adsorbent like this. I've seen earlier also. These two is the example we have seen earlier. This is the absorption on porous material, where you can see the hysteresis, right? You don't see hysteresis for micropores, and you also don't see hysteresis for the non-porous material. And the other type of absorption isotope that you can see is type, this is called, you can see the type there, type 1, type 2, type, this type 4, this is type 4, absorption on porous material is type 4, the absorption on non-porous material is type 2, the absorption on microporous is type 1, right? And you can have other type of absorption like type 3 here, right? So this is absorption on low affinity adsorbent, right? So meaning that the interaction between the adsorbent and the absorbent are not so strong, and you can get this type of absorption. Where the absorption, you can see after you have given quite high pressure, only the absorption can occur, right? After a certain high pressure only, high relative pressure only, the absorption can occur. And you can have this type of absorption also, which has hysteresis, right? You can also have hysteresis. This is low affinity absorption with hysteresis. So meaning that this it probably contain pores. It probably contain pores where you need a relatively low pressure for absorption to occur. And you can also have this type of absorption where it form multi-step. It form multi-step absorption for example, absorption for noble gas. And this type of absorption is quite rare. You don't normally see this type of absorption actually, but anyway, it is occur, and then you form a stable pressure, and then after that it increase again, and go step by step, stage by stage, until the absorption finish. Right. So these are the type of absorption effluent that you can get from the BET isotope. And this is classification, as the have shown also. These are the pore classification also given by IUPAC, the size of pores. So normally you want to use this classification. Normally you want to use this classification for this to classify the pores of your material. Whether you want to say it is in micropore range, whether it is in mesopore range or micropore range. Okay, physical pictures of pores or porous or porous solid. You can have many type of pores. You can have the cylindrically blind pores. You can see here. So where the pores, you can see the pores, and then you can see that the pores is blocked there, right? So it is a cylindrical blind pores. You can have like cylindrical pores where the type, cylinder type, and it is open end from one to the other end of the material. And you can also have true pores. Probably it is not a cylindrical type, but it's true pores also, where it open to open on one side, right? So you can have space roughness. You can also have closed pores. You can have closed pores. This pores, of course, is not accessible by the absorbent because it's inside the material. You can also have other type of pores, slit, and also tunnel or funnel-like pores. Funnel-like pores. You know the funnel, right? Funnel-like pores, right? You can have slit pores, very slim pores, right? So these are the type of pores that you can have in the materials. For example, if you have like characteristic carbon, you can have a lot of type of pores, that some of the pores are actually some of these pores you can find in the carbon. Okay, so how do we know what type of pores in this material or in the adsorbate, in the adsorbent, right, or in the substrate? So we can compare our isotherm to the isotherm given Du Bois. Isotherm given by Du Bois. This is called as Du Bois hysteresis loop. Du Bois hysteresis loop. So we for the hysteresis, you can actually assign this loop to the pores, right? So for example, type A, for example, type A with this type of loop, this type of get for the pores is this the type of pores for type A, right? So you can actually assign the type of pore that you should get, that you should be getting with the hysteresis loop that you get for the absorption isotope, right? So meaning that from your study, you get the hysteresis loop, and from there you can actually predict. You can actually predict. This is probably not exactly. You can actually predict what is the type of pores that is there in the material. All right. So for each one, right? For B, for C, can actually so for example, for like if it is A, if you get the absorption which is looks like A, then you can say that your pores include tubular capillaries, tubular capillaries with slightly widened parts. We don't know which one. We don't know which one. Actually, just sign, or you can actually predict what type of pore that you should be getting for this kind of isotope. For example, you get type B. You get type B. This is the type. So the pores should be open slit shape capillaries with parallel walls, with wide bodies and narrow short necks. So these are the interpretation of this isotome from the isotome that you can actually use. You can usually use this to interpret or to say something about the pores inside your material, right? So of course, you need to do you cannot when you do your research, you have got this type of the type of isotopes, then you can compare with the explanation or with the uh, description, with the description of the pores, and then you can say your pores is like this, and so on. This is not the physical. We don't see this. We don't see this. This is only interpretation based on the isotope that you get. All right. Okay. So catalyst rate, that is the topic for the next chapter. So we're going to move on to the next chapter on this catalysis reaction. Okay. Or space reaction, we call it space reaction rather than catalysis reaction, space reaction. I'll take break for 1 minute to take some water. Okay, we can move on now to the surface reaction. Right, so this topic is actually very much related to the previous one, which is on the absorption. So some of the things that you see here, you can see very highly related to the previous topics. Of course, because this is surface reaction, and for surface reaction, the reaction will involve absorption process. Reaction will involve absorption process, and in fact, the absorption process itself can be considered as the surface reaction. All right. So this the adsorbate, you have adsorbate, adsorbent, you have adsorbate, all right, adsorbate come to the adsorbent and get adsorbed on the surface. This can be considered as a process also. So because the adsorption process can occur by normal physical adsorption or by chemical adsorption. If it involves chemical adsorption, then it will involve a strong bond between these between the adsorbent and the adsorbate, and sometimes it also involves breaking of bond, formation of formation of strong bond, and overlapping of orbitals. So that is very strong adsorption process when it involves chemical adsorption process. So so normally if you have adsorbent, for example, A2, like A2, and the say adsorbate, adsorbent, say D, right? So what you'll get is that this A to D, the formation of the bond between the adsorbate and also the adsorbent, right? And of course, this one for certain type of adsorption, the process is reversible, where the desorption can occur by giving certain amount of pressure. You can actually dissolve the adsorbate from the adsorbent, and you can reverse the process, right? Okay, surface reaction. Many reactions are catalyzed by solid surface, right? So many reactions catalyzed by solid surface, meaning that after the reaction, after the adsorbate adsorb on the surface, you have adsorbate A, for example, adsorb on the surface, and then you have adsorbate B, adsorb on the surface, and these two adsorbate fuse to each other and then react to form a different compound. For example, AB. AB. Right? So the reaction is actually catalyzed on the surface. Reaction is actually catalyzed on the surface, and the surface has been this, or the adsorbate has been the surface to which the reaction can occur easily. If you let the reaction to occur in the gas phase, it will not occur. But if you let it adsorb on the surface, it will occur easily. So the surface is then catalyzing the process. So the reaction takes place more readily on the surface than in the homogeneous phase, all right? So the coordination number of atoms or molecules at the surface is lower than the coordination number of atom in the bulk. Yeah, so that there is high propensity or high tendency for the reaction to occur. What does it mean? Reaction may act as step in the catalytic cycle molecules, and atoms can attach to the surface in two ways. All right. So what does it mean that coordination number of the atoms on the surface? So if you see the adsorbate, so this is the surface of the adsorbate, for example, right? And below here is the bulk of the adsorbate. sorry, the adsorbent, not adsorbent, the bulk of the adsorbent, right? So you have the adsorption occur on the surface, right? The gas molecule, for example, on the surface, right? And of course, this gas molecule that is on the surface is interacting only with the surface. Only part of the molecule is interacting with the surface, not the whole molecule, right? So that's why it says here that the coordination number of atoms on the surface is actually lower than the coordination number of atoms inside or in the bulk of the material. So you have got the interaction with all sides if it is inside the material. If it's on the material, it's just on the surface. All right, so desorption can occur by phase desorption, as we have seen earlier in the previous discussion. Phase desorption involves van der Waals interaction, very weak interaction, or example dispersion. Example of this dispersion of the adsorbate on the adsorbent, or the gas molecule on the substrate. Polar interaction is one of considered as the physical adsorption between adsorbate and also the substrate, right? All right, so just to substrate and also the adsorbate. So sometimes I use the word substrate, sometimes I use the word absorbent, which means the material, the adsorbent. So this is the substrate. This is the surface of the substrate. Or this is the adsorbent. This is the surface of the adsorbent. The adsorbate is, right? So that is the adsorbate. Or you can also refer to that as gas molecule, for example. The gas molecule is adsorbate, which is the substance or the materials that is absorbed on the surface or the substrate or the adsorbent. So van der Waals is a long-range interaction and weak interaction. So the binding energy is around 20 kilojoule per mole, and the distance of the interaction is within 4 to 10 Armstrong. This is quite large compared to the chemical adsorption that we will see later. Okay. So it can also involve overlapping of orbitals, small overlapping. That's why it is not a strong adsorption process. Okay, and as we have seen earlier also, when the adsorption occurs, right, the adsorbate still retain its original identity. Its original identity, meaning that the adsorbate doesn't change in terms of its chemical identity. If it is gas, nitrogen, for example, adsorbed on the surface, it is still nitrogen, right? So there's no bond break and so on, right? There's still nitrogen on the surface. So it can be adsorbed like this, can also probably adsorb like this, for example, right? So, but it's, the identity of nitrogen gas is still nitrogen. So, the fusion adsorption process, the adsorbate identity when it adsorbs on the surface. Chemisorption, on the other hand, all right. So molecules stick on the surface, forming chemical bond. Forming chemical bond, and the other thing is that it tends to find surface site that will maximize its coordination. Will tend to seed coordination, right? So meaning that after the absorption occur, this molecule which is absorbed on the surface will try to find a space or a site where it can form strong bond with the substrate. So the binding energy involved is rather high, 200 to 500 kilojoule per mole as you compare to the previous one, only 20 kilojoule per mole. And the distance of interaction is very, very small. It is between 1 to 3 Armstrong only. So that shows, that's what makes strong bond or strong interaction between this substrate and also the molecule. And it involves large overlap. It involves large overlap between the surface of the substrate and also the adsorbate. So if it involves the orbital overlapping, so the orbital overlapping is much larger compared to the one for physical adsorption. Semi-subspecies may be torn apart at the demand of unsatisfied valencies of the atoms. Meaning that in order for the adsorbate to be absorbed on the adsorbent by chemical adsorption, right? So they have to match the valency or the overlapping of the orbital. So they probably bond breaking occur. And the material is torn apart. So chemisorption is basically exothermic. It's a certain process, right? So spontaneous process at constant temperature and pressure requires delta G. So the delta G involved we have seen earlier for absorption, either it is for chemisorption or physisorption. So the delta G is negative, right? And then since we are talking now about the catalysis reaction or the reaction on the surface, so we're talking more about the chemisorption process. And of course, the delta G is also negative. And on desorption, the translational freedom of the substrate is reduced. So that's why delta S is less than 0 also, meaning that the S value, the entropy value after the absorption is less than the entropy value before the absorption process. Of course, that is clear because before the absorption it is in the form of gas and also the solid, and when they absorb on the surface, it has become one. So meaning that this the adsorbate is on the surface, and of course that is the stage where the entropy is less than the entropy before the absorption process. So if you try to get the H value, the H value for the process is also negative. They are all negative, right? This is the wrong equation, right? So should be T there, should be T. Right? So dissociative chemisorption may be not activated or maybe non-activated or activated adsorption process. So what is activated and non-activated adsorption process? Okay, so let us look at this what I call as this curve of energy versus the distance from the surface. Energy versus distance from the surface, right? So this is energy axis, and the distance from the surface r, right? So for the for
for the physics absorption process, for the physics absorption process, so you have got molecule, say A2 molecule. A2 is the molecule, right? A2 molecule, so you can see this is the molecule here, right? So A2 will be approaching the surface to a certain distance from the surface. You can see the energy drop and reach a minimum. So this is where the interaction occur between the gas and also the surface, and it form bond. Not a strong bond. It is only a physical bond. For example, van der Waals interaction between these two materials, the gas and also the adsorbate or the substrate, the adsorbent or the substrate. Okay, so you can have another type of the adsorption process in this way, where the reaction can occur on the surface, right? Reaction can occur on the surface, and this is molecule A2 absorbed on the surface. After molecule A2 absorbed on the surface, right? So it will diffuse to a different site on the surface to form a chemical bond with the surface. So meaning that this is where physical adsorption occur, but at the same time the molecule try to find a place where it can form chemical bond to the surface, right? So so this is called as non-dissociative adsorption process. Non-dissociative adsorption process. So these two, physical and also chemical adsorption process, are non-dissociative adsorption process. But there are other type of chemical process that can occur also. This is called as dissociative chemical process. So meaning that the gas molecule that is absorbed on the surface, right, in form of A2 on the surface, right, will try to find a space where it can form chemical bond with the surface, but at that site, so the molecule actually split into atom A and A to form the bond with the surface. So meaning that the reaction occur or the adsorption occur, but at the same time followed by dissociative process, dissociation process, where A is split into the atoms and adsorbed on the surface. So this is called as dissociative adsorption process, or we can call it as non-activated. Non-activated. This is non-activated dissociative adsorption process. So this is the previous one was non-dissociative adsorption process. This is non-activated dissociative adsorption process, and we have another one. We have another one which is called as because as activated. This is activated dissociative adsorption process. So why it is called as activated dissociative adsorption process? In order for the adsorption of the molecule of the atoms to occur on the surface by chemical adsorption, the molecule have got to go through an activation process. The activation energy have got to go through an activation energy before it can form. It can have got to go through, to pass or to overcome. They got to overcome a certain amount of activation energy before it can form the bond with the molecule through chemical adsorption. Okay, So this is called as activated dissociative absorption. Then you have got non-activated dissociative absorption. You have non-dissociative absorption, non-dissociative absorption, and you have got another one which is only fuzzy absorption, right? Okay, so let's just move on. All right, so physical absorption, chemical absorption, dissociative absorption, whether it is activated or non-activated. Mix, and they absorb molecule on the surface, right? So the absorb molecule on the surface, they are dynamic, they don't stay there, they can diffuse from one place to another to find the right site for them to form bond with the substrate, right? And at the same time, so they can dissolve. So these are the process that can occur. They can dissolve. When they absorb, they can also dissolve, right? They can also dissolve back into the surface, or they can diffuse to a different place, and this may vary with temperature, right? So if you apply different temperature, so you get a different reaction occur, or probably the reaction will be faster, for example, and diffusion will be better, and also the desorption will be easier, right? So especially when you talk about the absorption process, the absorption is normally, especially for physical absorption process, for physical absorption process, the absorption is when if you lower down the temperature, more absorption will occur. But if you increase the temperature, less absorption will occur, and more desorption will occur for the case of physical absorption. For the case of chemical absorption, what is happening is that it is the reverse, right? So as you give more high temperature, you give high energy for the material to form bond with the substrate, and that will induce more absorption rather than desorption. So absorption or chemisorption may involve more than one type of molecule or atom, right? For reaction to occur, they have some degree of mobility, right? Absorption or chemisorption may involve more than one type of molecule or atom. Okay, this is clear from the statement there. So you can have a different type of molecule absorbed on the same surface, and and then this molecule can interact with each other to form a reaction, meaning that the molecule itself, not the molecule at the surface, the molecule itself, which is absorbed on the surface, as I shown you earlier, they can come together and react to form a different molecule on the surface. All right, so this is called as of course, these are the things that we are looking at on the surface reaction. So we have seen this on the Langmuir theory because this topic is very much related to Langmuir theory. Because it involves a Langmuir absorption process. So in Langmuir absorption process, we know that there are a number of assumptions that is done before they get to the theory. Okay, among the assumption is that the absorption limited to only one monolayer, right? The absorption is limited to one monolayer. So it is not really applicable to physical adsorption process, it is more suitable for chemical adsorption process. Okay, and surface force is short range. All the molecules striking the bare surface is absorbed. Other molecule reflected back into the gas phase. So this is really indicating that it is a chemical adsorption process. So only the molecule that strike the surface will be absorbed. The molecule which not strike the surface, for example, if you have a molecule on the surface, they will absorb. Okay, but you have other molecule which strike on the molecule that is absorbed on the surface, will not be absorbed, but will be bounced back into the gas phase. Okay, so at equilibrium, the number of molecules evaporating is equal to number of molecule condensing. So we have gone through this, and we have also come to having this equation, what we call as the Langmuir equation that we have seen earlier in the previous chapter or in the previous topic. So it is also important to also see how this last equation or the Langmuir equation, this is also Langmuir equation, this is also Langmuir equation. Yes, a Langmuir equation, right? So only that this is not in a linear form, but form, right? This is in linear form where you can plot PV or you can plot PV versus P. You can plot PV versus P, right? PV versus P in order for you to get the slope of 1 over V, right? Slope of 1 over V, right? The slope of 1 over V and the intercept of 1 over VE, right? So from the slope, you can get the value of Vm. From the intercept, you should be able to get the value of B. So what is important of B to you? Because B is related to the energy of adsorption. So that's why B value is also important, especially in the case of when we talking about the catalytic reaction. When talking about catalytic reaction or surface reaction, the V value is also important for us to evaluate, so that we know what is the energy involved in the process. So you can get the value of B, and from there you can get the value of delta H, because the other values are all constant, and also temperature, that you should know what is the temperature that we have done the process. Are you still with me? Are you feel tired? Are you okay?
Yeah.
Yes, Prof.
Yes, sir.
Okay,
All
Prof.
right. Okay. Good. All right. Okay. Okay. So we move on now to so these are the isotherms. So you can also have isotherm. This is also isotherm. This is also isotherm. The plot here, this is also isotherm, but it's not in a straight line plot. Now it is Vm versus P over P naught, or the amount absorbed. Not Vm. The amount absorbed versus relative pressure. So this is if you look at the here, so you can just take this equation. So the amount absorbed V versus the pressure, versus the pressure. So that's why you get a curve rather than a straight line. So you can make the equation to straight line, and you can get the value of Vm and so on from straight line. So this is good when you do the VET isotherm. You do VET isotherm, you want to look at what type of isotherm, whether it has hysteresis or non-hysteresis, right? Whether it has what type of hysteresis loops that occur on the surface. So you will do, or you plot VM, or you not VM, you plot moment absorbed, not VM. VM is this value, right? You plot the moment absorbed versus the relative pressure. And from there, you can see the isotherm, whether it is non-porous material, whether it's porous material, whether it has hysteresis or non-hysteresis. From there, you can get the picture of what type of force inside the material. All right, so I've gone through this. I don't have to repeat on this one. Okay, also this one. This is actually given as the assignment to you to do. So catalysis rate. Okay. Okay, reaction catalyzed by solid surface. So the rate is determined by the amount of gas absorbed or the fraction of the active site covered. All right. So meaning that the rate will depend on theta, right? So we have seen earlier what is theta, right? Theta is this is theta, right? Theta is V over Vm, because Vm is the total surface covered, and V is the surface covered at certain pressure, right? So meaning that the extent of coverage, the extent of coverage is given by the value theta. And the rate of reaction, will depend on the amount of surface coverage, right? So it will depend on the amount of surface coverage. So meaning that rate then is proportional to the surface coverage. So then just give K so that you can relate rate to the surface coverage. Okay, so rate is equal to K theta, and theta is V over Vm. And if you refer back to the previous one, the Langmuir equation, so you can see that V over Vm is actually this, right? V over Vm is actually this one, and V can be related to the enthalpy of absorption, right? So you can see that K, B, they're all constant. K and B are constant. So if the reactant gas is strongly absorbed on the surface, especially when it is at high pressure, right? So then at high pressure, meaning P is very high, Vp plus 1 is Vp. So meaning that the rate is only equal to K. The rate is only equal to K, and this is the case of zero order reaction, right? In the case of zero order reaction. And if the reactant is weakly absorbed, if the reactant is weakly absorbed on the surface, especially when the pressure is low, when the pressure is low, meaning Vp is low, Vp and 1, Vp plus 1 is only 1, so meaning that R is KVP, right? So Vp plus 1 is 1 because Vp, P is low, Vp, V times P is very low. 1 plus Vp is basically 1. All right, so then rate is KVP. And you can see that rate is proportional to P to the power of 1. So this is then is first order reaction. So meaning that at lower pressure, it is first order. At high pressure, it is zero order. And there is a stage where you have the rate at the intermediate rate. Should get here. Right. Okay. Let's go on through this first. So reaction can can be followed by monitoring the change in pressure of reacting gas. So rate then is dPA dt, where PA is the pressure of the reacting gas. So PA is the direction of the reacting gas. So dPA dt is K prime PA at low pressure, right? And then K prime is where K prime is KKB, and the integration will give this equation, right? So you also know that this is equation for first order reaction, right? So this is of this reaction in case of the reaction occur on the surface, occur at low pressure. So low pressure first order, and you can have another one which is a rate is equal to dPA over dt, also equal to K. This is the case where it occurs at high pressure, right? And if you do the integrated form of that is PA not minus PA equal to KT, right? And this is, you know that this is the integrated form of reaction at the integrated form of this zero order reaction. All right, so there's also intermediate case. Intermediate case, meaning that after the first order before the zero order. There's a case where you have intermediate case. So you have low pressure, you have high pressure. High pressure, right? So, and then you have intermediate pressure, right? Intermediate pressure. So this is where you have first order, sorry, this is where you have zero order, zero order reaction. So this is where you have first order, and this is where you have got intermediate order. So in between the high and low pressure, you have another one, which is not first order, not zero order, but it is actually a combination of both. The combination of both first order and zero order. So at that stage, dPA dt is equal to K times Bp over 1 plus Bp, the original equation. And if you do the integration, you get the integrated form of the equation. So you can see that you get an integrated form of equation like this one. So you can see that this is a combination of two parts. Now one part is for the first order, the other part is for the zero order. So the combination of two parts at that stage. All right, so if you do the plot of the amount absorbed or the surface coverage, the surface coverage versus pressure, this is the plot that you will normally see. And this is the area where it forms first order. You can see that the theta versus P is straight line. It's almost straight line, right? And then it curve a bit. Here, this is where it is intermediate stage, right? And then before it form a horizontal line here where it is zero order. So this is where it is high pressure, right? This is at high pressure, this is at low pressure, and this is at intermediate pressure, right? Okay, so then we can move on then to dissociative adsorption process. Dissociative adsorption process is a process where when the adsorbate or the gas molecule right? The gas molecule absorbed on the surface. Let's say S is the surface, and then dissociation occur. Then the atom, gas atom absorbed on the surface, right? So we need the one is absorbed on the surface is the atom, the gas atom. So this is dissociative absorption process. So the kinetic of the equation that can be written for this type of process is, of course, the absorption will the process will is written as d theta dt, because the process will depend on the rate of the surface coverage, right? So the rate of the surface coverage, you can see there are two processes here, right? One is the absorption process, right? So which depend on the amount of empty surface, right? The absorption process which depend on the amount of empty surface, and the desorption process which depend on the amount of absorbed surface, right? So the amount of absorbed surface is theta. The amount of empty surface is 1 minus theta. Okay? Right. So then, so one is the absorption process, one is the desorption process. So d theta dt then is equal to Ka Pa 1 minus theta square Kd times theta square, and this is for the case of this type of process, which is we call as the dissociative absorption process. Okay, so and at equilibrium, d theta dt is 0, meaning that when it reach equilibrium, right? So the rate of forward and backward reaction are equal, and at that stage, the d theta dt, you plot theta versus times, you can see that it is it forms a straight horizontal line, and d theta dt is 0, and then we can then get this equation, right? So theta square over 1 minus theta is equal to Kpa over Kd, and since Ka, which is the rate constant for the forward reaction, and Kd is the rate constant for the backward reaction, and K is just Ka over Kd, right? So then we can replace Ka over Kd, which is K, which is the equilibrium constant, and then we can then rewrite the equation for this type of reaction, or we can write the the relationship between theta and K and also Pa for this type of reaction as shown, right? So it is not difficult to get from here to here. Okay, you can show that. How do you get this equation from the previous one? So remember, this is case of dissociative absorption, right? Dissociative absorption, where what happened in dissociative absorption is that A2 absorb on the surface and at the same time dissociate into atoms to form for the absorption to occur, right? Okay, so move on now to the next one, which is non-dissociative competitive absorption. Okay, so this is non-dissociative, meaning that the molecule that is absorbed on the surface, the molecule that come to the surface is not dissociate, not dissociate into atoms, but If it is in atom form, it will if it is in atomic form, it only will absorb the space. If it is in molecular form, for example, N2, NN, so there's no bond breaking between the atom. There's no bond breaking occur. So the gas absorb on the surface, and another gas come and also absorb on the surface. There are two gases together. There are two gases together. Absorb on the surface, right? And there's no bond breaking. They are in their original form. When they absorb on the surface. But at the same time, they are competing for the space to be absorbed, right? So A and B are competing for the site to be absorbed on the surface. So which one will win will depend on the affinity of each molecule to the surface. Okay, then we can write the equation. Now you can see that there is no square here, right? So because this is non-dissociative absorption, non-dissociative absorption, and they are competing between each other, right? As you can see from here is that d theta dt, and the absorption will depend on the site available. And the desorption will depend on the amount absorbed, right? The desorption will depend on the amount absorbed, right? Okay. For A, for the rate of desorption of A, will depend the absorption will depend on the amount. So the desorption will depend on the amount absorbed. For the desorption, the absorption will depend on the space or the site available. So the same for B. The same for B. Right? So only that for B, you have theta B for the case of the desorption. And at equilibrium again, both will be the same, since this is, we are considering only the the absorption. We only consider the absorption. There's no reaction between A and B yet. No reaction between A and B yet, only the absorption, right? Right. So then we can have the amount of A absorbed is equal to the equal to this one, and the amount of B absorbed is equal to this. Right? Okay, so we have seen two, right? So one is on this dissociative absorption, the other is on non-dissociative competitive absorption. Take some water. So we're going to move on. All right. So what you can do is, how do you get from this part to these two equations? So you can do the derivation yourself. You can do the derivation yourself to get theta A and also theta B. Okay. Isosteric enthalpy of absorption. That is the value of delta H of absorption that we have seen earlier. All right, so you can actually evaluate the value of delta H. Okay, so the standard enthalpy of absorption at fixed surface coverage. For example, you know a certain surface coverage. You want to know the value of delta H at certain surface coverage. Say like you want to know the surface coverage at 0.5, say, or 50% coverage, 50% coverage, or 40% coverage, for example. You set the coverage. Say like you want to know at 50% coverage, and that meaning that you have fixed. Oh, low battery. Let's say you have fixed that at like 50%. You can also fix at different value. You can also fix at like 40%, 30%, and so on. But you fix a certain space coverage. Okay. And theta increase with increasing pressure and approaches 1 at full coverage, right? At very high pressure. Different curve is obtained at different temperature, right? So you have different temperature, you can get different curve. And you can get, for example, if you plot, see, if you plot space coverage versus pressure, for example, right? So you can get like this, you can get like this, you can get like this, and you can get different curve at different temperature. So meaning that you can get, for example, at high temperature, for example, the reaction probably will be better, and you can reach equilibrium faster than at low temperature. Okay, so the temperature depends on K constant and can be used to determine the value of delta H absorption. So you can use Van Hoff equation. I'm not sure whether you have gone to Van Hoff equation. Probably if you taken 3101, you have been introduced of Van Hoff equation, right? Okay, so this is the equation that I've seen previously from the Langmuir plot. So you can get d ln k over dt is equal to delta AD over RT squared. And from Langmuir isotherm, we have this equation, right? Have you seen this equation earlier? I think so. We have seen this equation, right? And since theta is constant, theta is constant because we have fixed at certain amount of coverage. So we consider theta is constant. So meaning that ln k versus plus ln p is a constant. It's a constant. So then we can rewrite this equation into this form, right? So we have d ln p over dt is equal to negative non k over dt, and this is also negative. This check, this is negative because d ln k over dt is equal to delta dh over rt square. So meaning that d ln k minus over dt then is, so meaning that you have able to relate. We have been able to relate the d ln p dt with the delta h, right? So and then you can rearrange. The equation into this form. You can rearrange the equation into this form where you have d ln p over d1 over t at certain surface coverage equal to delta h over r. So what does it mean from this equation is that if you plot non-p versus 1 over t. So the slope of the graph that you get, it should be negative, right? The slope of the graph that you get is delta h over r. Delta h over r, and from there you should be able to get the value of delta h, right? Okay, so for that you are given this data. Okay, use this data to get the value of delta H. Data show the CO obtained at volume absorbed of 10 centimeter cube. It is not given as a percentage, but it is given in form of the amount absorbed on the surface. The amount absorbed on the surface is 10 centimeter cube, right? So this is the data given, right? So from the data given, so you should be able to get the value of delta H by using this equation. So this is called as 1/2 equation. This is actually 1/2 equation. This one is 1/2 equation. Okay. Okay, so I think we should be able to do that. All right, so we have a few minutes more. I'd like to just discuss on this one. So once the molecule absorbs on the surface, it tries to find a suitable site for it to absorb. At the same time, it can also diffuse from one place to another. For the reaction to occur, it is better that the molecule is easily diffused from one place to another to meet another molecule for the reaction to occur, right? So that will depend on the interaction between the molecule and also the adsorbate. So molecule with strong adsorption will not allow diffusion to occur, right? Molecule with intermediate strength of adsorption will allow partly the molecule to be diffused to one place, from one place to another. And so that the reaction can occur. That's why the molecule which is not strongly adsorbed can diffuse, and that will then induce a high rate of reaction. Right. As you can see from here, this is log rate of ethene hydrogenation on metal. So you have got different substrate here: niobium, molybdenum, ruthenium, rhodium, palladium, right? So you can see here, so the rate of reaction is different for different substrate or different catalysts. For niobium, this the rate is very low. Molybdenum a little higher than niobium, but the highest one is for ruthenium. So because for ruthenium, the adsorption can occur, but not so strong on the surface. It allows the diffusion to occur, and with diffusion, the reactant can meet each other at the sites for the reaction to occur. So meaning that there should be a balance between the desorption and also the diffusion, right? So if a desorption is too high, then diffusion will not be able to occur, right? If desorption is too low, meaning that the absorption is too strong, also it is not good, right? So there should be a balance between diffusion and desorption process, right? So the range that is good for that is between 0.1 to 0.2. The difference between the desorption and also the diffusion. Or if you can write in terms of E over E result is between 0.1 to 0.2. Okay, so meaning that it should allow a certain amount of diffusion to occur. Huh? Right, so the defect structures or sample may also play a dominant role because motion across terrace is easier than along footstep, right? So if you have a surface which is a flat surface, it's even easier if compared if you have a surface which is not smooth. So for example here, so it is not smooth, it cannot go up here, for example, right? So these are steps occur, then the movement along this type of surface is more difficult than movement along this surface. So meaning that this type of surface will allow better diffusion to occur, and this type of surface will not allow diffusion or better diffusion to occur. So meaning that surface mobility depends on the lattice planes that is exposed to the exorbit. All right. Okay, I think we can stop. You can stop there. It is 9:53. So remember also to click on your attendance, and you can see from here. So there are a few things that you should do from your DIY. So please take note. You can also take so probably I'll give you another set of DIY questions for you to do later, right? So until we finish, I think wait until we finish the this topic, right? So this is one part of the DIY question that you can do. I think I have also shown you earlier equation, how to derive equation, how you reach a certain result of derivation. That also can be part of your question for you to answer. Okay. All right. So we have another week to go. One more week to go. We have this topic and another topic that we should be finishing. I think we'll take another session, or probably we have got to take the Amali time next week a little bit for further discussion on the topic that we have discussed for my sessions. Starting from the beginning of the homogeneous reaction, enzymatic reaction, acid-base reaction, this absorption process, the catalytic reaction, and also the final part will be on the fast reaction, right? So hopefully we can cover all the parts next week, inshallah. Right. Any questions? Right. If there's no questions, then we probably have got to get yourself prepared for the next lecture. Right. So then we'll stop there for today, and I'll see you again, inshallah, next week at the same time.
Thank you, Doctor.